/watch?V equals CACLU 4 WWL1G. The 75 tandem cold rolling mill is a high-capacity unit used for reducing steel strip thickness with extreme precision. The process begins by loading pickled steel coils, typically 1.5 to 6.0 millimeters thick and up to 2,000 millimeters wide, onto coil carriages. Each coil can weigh up to 45,000 kilograms with a maximum diameter of 2,150 millimeters. Operators align the strip using hydraulic uncoilers and thread it into a rotary drum shear that trims the leading edge for smooth entry. Entry bridle rolls and loopers maintain consistent strip tension. The 75 rolling stands, often configured as 6 high units, progressively reduce thickness in a single pass. Strip speed ranges from 300 meters per minute at threading to 1,500 meters per minute during rolling. Automated gauge control systems adjust the roll gap up to 60 times per second to ensure thickness tolerance within plus or minus 0.005 millimeters. Human oversight remains critical for threading, roll changes, and monitoring loop stability. This setup enables precise, high-speed production of cold rolled steel, exceeding 1 million tons annually. The curved panel welding process is widely used in shipbuilding to assemble complex, three-dimensional steel panels. Panels measuring up to 14 meters in length are positioned onto precision welding tables with hydraulic clamping systems. Automated gantry welding systems, equipped with robotic arms, deliver travel speeds of up to 500 millimeters per second and maintain torch accuracy within plus or minus 1 millimeter. Offline CAD programming enables weld paths to be generated in under 10 minutes per panel, minimizing downtime. Robotic gantries operate with a positioning tolerance of less than 0.5 millimeters across workspaces as large as 12 by 5 meters. Each system can control up to 8 robotic welding arms simultaneously, achieving arc-on times exceeding 90% during operation. Operators oversee loading, alignment with tolerances of plus or minus 0.2 millimeters, and conduct quality checks. Weld quality is verified through arc signature monitoring and visual inspection, ensuring no porosity or misalignment. This advanced workflow enhances precision, reduces cycle time, and improves output for large-scale hull structure production. The LC4000 is a heavy-duty gear machining solution designed for manufacturing large-diameter, high-precision gears. It is used in sectors such as wind energy, shipbuilding, mining, and power transmission, where gear sizes often exceed standard machining capacities. This system accommodates gear blanks up to 4,000 millimeters in diameter and weighing up to 36,000 kilograms, supporting oversized components with complex geometries and tight tolerances. The machine features a 70 kW Hob spindle, capable of operating at speeds up to 1,500 revolutions per minute. Its direct drive rotary table holds loads up to 45,000 kilograms and rotates at speeds of up to 1,400 revolutions per minute. Gear face widths up to 1,800 millimeters can be processed, and a module range of 1 to 40 allows the production of fine pitch to coarse tooth profiles in a single setup. This flexibility is key for industries that require varied gear types without extensive retooling. A major advantage of the system is its ability to combine multiple operations into one machining cycle. These include hobbing, profile milling, internal cutting, and chamfering. The internal cutting unit is powered by a 53 kW motor operating at 250 revolutions per minute. A separate 70 kW chamfering spindle prepares gear edges precisely without repositioning the part, reducing total cycle time while improving alignment between features. Automation enhances productivity. A swivel loader performs part changes in just 1.4 seconds. The automatic tool changer swaps tools in less than 3 seconds, minimizing interruptions. All operations are managed through a 5-axis CNC interface, that supports real-time diagnostics and adaptive toolpath correction. Dimensional accuracy is ensured with a built-in measuring system. Probes inspect gear geometry during machining, and the system adjusts toolpaths dynamically to maintain tolerances. Final gear quality consistently matches AGMA Class 12 to 15 or DIN Class 3 to 6. Inspection data is stored digitally for full traceability and compliance with customer specifications. This machining solution combines structural capability, process integration, and advanced automation, enabling manufacturers to produce large, complex gears efficiently while ensuring high-quality standards across all production cycles. Hot wound springs used in subsea systems are engineered to perform under extreme pressure, corrosion, and cyclic loading. They are manufactured from alloy steel bar stock with diameters ranging from 0.562 to 1.75 inches, 14 to 44 millimeters. The steel is first heated in a walking beam furnace at 1,750 degrees Fahrenheit, 954 degrees Celsius. This furnace operates at 1.65 million BTU per hour, offering higher efficiency than older designs that consumed up to 12 million BTU per hour. Once heated, the bar is formed into a spring using a CNC-controlled coiler that wraps the material around a mandrel. This automated system can process over 125 metric tons of raw steel per month, supporting consistent quality and throughput. After forming, the spring cools in a controlled environment to 500 to 600 degrees Celsius to reduce internal stress. Tempering follows at 400 to 550 degrees Celsius for 1 to 2 hours, enhancing toughness and achieving the required Rockwell C hardness. The ends are ground flat for even surface contact, and the spring undergoes shot peening to introduce compressive stresses that improve fatigue life. Dimensional tolerances are held within plus or minus 0.05 millimeters. Final quality checks include hardness validation and non-destructive evaluation such as ultrasonic inspection to ensure structural integrity. Technicians are responsible for operating CNC systems, monitoring heat treatment, and overseeing quality control. The manufacturing space is divided into dedicated zones for heating, forming, and finishing to optimize safety and efficiency. This controlled process results in durable, high-performance springs capable of meeting the demanding conditions of subsea oil and gas operations. Seamless pipe production uses thermal induction heating and hydraulic mandrel expansion, followed by hydrostatic, eddy current, and ultrasonic testing for quality. I am Rechenquent. Hot forging involves heating steel to approximately 950 to 1,250 degrees Celsius for carbon types, or 1,095 to 1,150 degrees Celsius for stainless. Once heated, billets are shaped using mechanical or hydraulic presses, applying up to 160 meganewtons of force at speeds reaching 50 strokes per minute. Automated lines can deliver 90 to 180 pieces per minute, depending on billet size. For longer forging cycles, parts may be reheated to 950 to 1,200 degrees Celsius to maintain ductility. Controlled cooling follows, influencing final grain structure and mechanical properties. Forged parts typically meet tolerances of plus or minus 0.3 mm. Quality checks include ultrasonic and eddy current methods. Technicians and engineers manage temperature profiles, tooling alignment, and press operation for consistent output and safety. ASW. This industrial clay forming machine is designed for large-scale brick and tile manufacturing. The production process starts by feeding clay into a hopper, where a twin-screw system mixes and homogenizes the material. The augers range in diameter from 75 to 700 millimeters, allowing the unit to process up to 45 cubic meters per hour, depending on the clay composition and water content. A vacuum chamber located above the extrusion barrel removes air pockets before shaping. The chamber has been enlarged compared to previous designs, significantly improving de-airing efficiency and resulting in higher density, more stable extrusions. The screw mechanism, powered by a frequency-regulated motor, moves the material forward. Helical gears with dual-shaft transmission provide consistent torque and allow the machine to handle high loads during continuous operation. The interior is lined with wear-resistant components to extend service intervals. The clay is pushed through a precision die to form continuous sections, which are then cut to size using an automated knife system. Load cells and sensors monitor thrust pressure and machine performance, improving process control. Production zones include feeding, vacuum processing, extrusion, and cutting. Technicians manage system parameters, while maintenance crews benefit from modular parts and quick-access panels. This setup ensures precise shaping, high throughput, and reliable operation in demanding ceramic production environments. Blade production for turbines involves both roughing and finishing on 4 or 5-axis CNC machines. Materials, such as nickel-based alloys, are machined at cutting speeds between 40 and 80 meters per minute with carbide tools and up to 400 meters per minute using ceramics. Feed per tooth ranges from 0.1 to 0.5 millimeters, and depth of cut may reach 15% of the insert diameter. The sequence begins with bulk removal using high-feed milling cutters, achieving metal removal rates of several hundred cubic centimeters per minute. Final profiling is done to within plus or minus 0.05 millimeter tolerance. Grooving is performed using tools with internal coolant at increased cutting speeds by 10 to 50%. Operators supervise machining parameters, technicians manage tool wear and fixturing. Engineers handle coolant strategies and digital monitoring platforms for consistent, stress-free blade finishes. The installation begins with verifying anchor bolt layout and column elevation. Steel columns, generally 2 stories tall, arrive on site with welded side plates, deck angles, and a temporary spacer to maintain side plate separation. Using standard lifting methods like chokers or lugs, columns are positioned. Moment beams, fitted with cover plates and vertical angles, are guided between the side plates. The top cover plate is detailed to be 1/16 to 1/8 inch narrower than the flange, ensuring easier fit-up. Each beam end is temporarily secured with bolts before final installation using 6 high-strength fasteners. Once aligned and tightened, 4 horizontal fillet welds connect the plates to the top and bottom covers, while 2 vertical welds join them to the beam's vertical angles. After mechanical and welded assembly, Fireproofing is applied using spray-on material with either metal strips or mesh to bridge the beam column gap. Final protected zones are clearly marked. This advanced milling system is designed for shoulder, slot, and ramp machining, offering cutter diameters from 9.7 to 200 mm and depths of cut up to 15.7 mm. When paired with a damped adapter, it provides excellent vibration control during extended reach operations. The system uses internal mass damping to reduce chatter, allowing up to 300% higher metal removal rates over standard holders. It is especially effective when the overhang exceeds 4 to 5 times the cutter diameter. Typical spindle speeds range from 7,000 to 10,000 revolutions per minute, depending on diameter and setup rigidity. The cutter body is made using additive manufacturing, minimizing weight and placing the damper closer to the cutting edge. Internal coolant channels help with chip removal and thermal stability. Operators set feed rates, monitor cutting forces, and inspect insert wear. Technicians ensure proper installation of tool holders, conduct replacements, and verify machining stability using real-time vibration analysis tools. Spring deflects 97 mm under 3,560 kg force. Elastic limit reached at 3,810 kg force. Tested through 5 million cycles under variable loading. Hydraulic 4-roll bending machines are used to shape steel sheets into precise cylindrical or conical forms. These machines handle plates up to 3,000 mm wide, with thicknesses ranging from 10 to over 150 mm, and can form diameters as small as 1,400 mm. Typical rolling speeds vary between 1 and 10 meters per minute, depending on the material and setup. The process begins by aligning the sheet and performing a pre-bend with the side and top rolls. Technicians input settings via CNC control systems to define the curvature and cycle steps. The plate is passed through the rolls to complete the bend. Final diameter tolerances are kept within plus or minus 1 mm. Production lines are divided into loading, forming, and unloading zones. The video showcases the Midas tire factory in Otrokovic, Czech Republic, part of Yokohama, TWS. It presents a detailed look at the production process of large agricultural and industrial tires. Viewers are guided through raw material preparation, tire building, curing, at around 180 degrees Celsius for 16 minutes, and final quality checks. The facility is highly automated, emphasizing precision, efficiency, and environmental standards. The video also highlights the plant's scale, producing over 42,000 tons annually, and its role as a key hub for advanced radial tire technology. Steel blanks of 400 mm diameter and 1.2 mm thickness are deep drawn into pans using hydraulic presses rated between 500 and 2,500 kilonewtons. A typical setup uses 1,500. Flow-formed wheels start with an idea from the design team, who create concept sketches based on vehicle type, performance goals, and styling trends. The selected design is modeled in three This advanced cut-to-length line is designed to convert steel coils into precise flat sheets for industrial use. It handles input material with coil widths from 400 to 1,500 millimeters, thicknesses between 0.5 and 3.0 millimeters. The vertical bandsaw system cuts steel plates and blocks up to 1,000 millimeters high and 1,300 millimeters deep, using a blade sized 8,800 by 67 by 1.6 millimeters. Blade speed ranges from 15 to 75 meters per minute, powered by a 7.5 Gdora's Remscheid facility is a vital production center for premium hand tools, employing approximately 800 skilled workers and manufacturing over 18,000 different tool variants that are distributed worldwide. The plant combines state-of-the-art automation with traditional craftsmanship, ensuring that every tool meets stringent standards for precision. The Orion crew module arrived at Kennedy Space Center in June 2012 for manufacturing and testing. Over 2 years, engineers transformed the green shell into a fully functional spacecraft. The service module and protective fairings were also assembled. In September 2014,